All right, so colligative properties B. Sorry about that, I got interrupted and I haven't had time to um, edit the video together, splice it together. So at any rate, what's left? So we talked about the hypertonic and hypotonic situations within the living systems. Electrolytes in solution in colligative properties. So what happens if we have, for instance, sodium chloride and that dissolves in water? How is that different from dissolving, say, methanol? So on the left here we have sodium chloride, and over here we have methanol. So both of these things will dissolve in water. Both will lower the freezing point and raise the boiling point. The difference is when the methanol gets dissolved into solution, you only get one particle, 1 mole of particles per mole of methanol. However, with sodium chloride, if you put a mole of sodium chloride in, you actually get 2 moles of particles. Right? So you would think that, perhaps, well, then the molality in terms of the ions would be twice as much. However, you also have to consider the fact that that when the water molecules surround these things, so if we look at, for instance, this part right here, the hydrogen part is at the outside of those water molecules. So it's kind of a positive sphere around there. And around this one here, you'd have a negative sphere. Well, what happens then is that those two things are going to interact. And there's going to be some attraction there. So although you're putting 2 moles of particles into solution, it doesn't really behave fully like 2 moles of particles. It's going to be some ratio of that. So what we do is we don't abandon the equation, similar to where we didn't abandon the ideal gas law. We just added variables that would take into account those factors. So that's where we get the Van Hoff factor. So this change in the temperature of the freezing point, instead of being equal to just a constant times the molality, there's the Van Hoff factor times the constant times the molality. So that the freezing point constant stays the same for the solution, but the I, the Van Hoff factor, is characteristic of the solute now. And so here we have a number of values for the solute. Let me blow this up a little bit so you can see it a little better. All right. And as you can see, if we look at sucrose up at the top here, sucrose, the Van Hoff factor, doesn't matter what the concentration of the solution is, it's 1, right? Because sucrose, when you dissolve that into water, there's only one particle. Sodium chloride, if it's very concentrated, so now concentrated means that there's a lot of sodium, a lot of chloride ions, so there's more of an opportunity for interaction there. That Van Hoff factor is 1.87. So that's a reduction from the 2.0. So the molality of the sodium chloride would be, say if you had 1 mole of sodium chloride in 1 liter, 1 kilogram, it would be a 1 mole solution. The Van Hoff factor would take into account that 1 mole solution breaks up into 2 moles of particles. However, again, if that molality is 0.1, you don't actually get 2 whole particles worth of increase in the change in temperature. You only get 1.87 of that 2 moles. Okay. Now, obviously, if you got to very, very small concentrations, you notice that as we get over here to the very small concentrations, that it gets closer and closer to the limiting value, which would be, if they're just, all the ionic particles just came apart. So we don't have to deal very much with this type of thing. We won't have to deal with it in the lab, but it is an issue that you could run into.